Alright, so today we're talking about quadratic equations. We'll spend a couple days on this stuff, going through our techniques for factoring. This is going to be kind of a refresher course for us in regards to factoring, but it is very important to be able to do, because down the road it's almost every problem involves some type of factoring eventually. Okay, so we need to be able to do this. And kind of like a good portion, I'd say about 70% of this class, maybe 65% of class, is actually developing a longer list of factoring techniques. So when you get to a calculus class, when you have to factor almost every problem maybe, you have different things you can pull from. You have the product sum technique, you have the AC method, you have factor by grouping, you have maybe the rational root theorem. So we'll learn those things and those procedures as we go through. So when we get to calculus and there's a kind of implied or understood factoring that needs to take place in the problem, you have all the factoring techniques and abilities to do it. Okay, so that's kind of the goal. When we factor a quadratic equation, okay, so kind of what's going to happen later in the 9 weeks, we're going to start talking about like cubic equations, quartic equations, so third degree, fourth degree, fifth degree. All of those we're going to factor, and we'll have separate techniques for them. But at some point, they will all factor down and eventually be left with a quadratic equation. So once we get to that quadratic equation, then we need to turn to this set of rules and procedures to finish the problem. Does that make sense? Okay. So a quadratic equation is an equation of the form ax squared plus bx plus c is equal to 0. Where a, b, c are elements or belong to your real numbers, and a cannot be 0. If a, start with the easy part there, if a is 0, the x squared term disappears, right? And you're left with bx plus c, which is just a linear equation. Okay, so that's why a has to be non-zero. But a, b, and c, okay, that weird looking e there, okay, this is a set notation symbol, which refers to the phrase is an element of. Sometimes people phrase it as belongs to. And obviously, that symbol represents your real numbers. Okay? Meaning that a, b, and c, they could be anything. We like them to be integers, but they could be rational numbers, they could be fractions, which are rational numbers, they could be pi, they could be e, maybe whatever they want to be. Okay? A lot of our techniques kind of hone in on hoping and wanting them to be integers, but if they're not, we still have some techniques that will address them. Okay, we'll go through those as we move on. When we come through some of these factoring techniques, I'm going to try to walk you through some logical proofs of why the techniques work, why we do them. Okay, and what allows us to do them. The quadratic formula is kind of your catch-all, right? That one will always get you your solutions. When we go through and we prove the quadratic formula, I don't know if you guys did this last year, we will actually start with that, okay, as our beginning object, and we'll work through completing the square on that. When we complete the square on that, it develops into the quadratic formula. Okay? Completing a square is a technique that will essentially always factor something for us. Okay? But it's it's an elongated kind of convoluted process where if I can do it with that generic ax squared plus bx plus c equals 0, it gives me a formula that I can just insert values, evaluate, and be done. Okay, so we'll work through those things. Those are the techniques that you're probably accustomed to. All right, when I say factoring, we're talking like GCF factoring, greatest common factor, pulling out the thing that all the terms have in common. We're talking product sum technique. Okay, so two numbers that multiply together give me the last term, and give me the middle term. We're talking the A times C method, or factor by grouping. And then we've got some key, or I guess unique situations with the square root property. It's basically, you can use a square root property when you don't have a linear term. We can do completing the squared, which will always work regardless of what we start with, and then the quadratic formula again will work regardless of what we start. So those are just some options and things that we talked about maybe in the past, and those are the things that we're going to try to target throughout this series of the next 2 or 3 days. Okay. When we talk about a quadratic equation, we have the ability to have multiple types of answers. Okay. And right now, we're going to try to decipher how many solutions we could have. Does anybody remember when kind of the most common amount of solutions would be what? Does anybody remember? 2. Okay. So a lot of times we're going to get 2 solutions. Okay. So I'm going to write 2. I'm going to write distinct real solutions. And when I say real solutions, I mean that they're solutions coming from the real number line. Okay? Graphically speaking, you guys might remember it looking something like this. A quadratic is always going to be what curve? What do we refer to it as? Parabola. Okay? So that would maybe be a situation where you have 2 distinct real solutions. That becomes one of my solutions, and that x value there becomes one of my solutions. Remember seeing that last year? Okay. But I can have other types of solutions. I can have one. Let's write it, one real solution. Okay. But it's going to be, and I'm going to actually draw the picture for you first to see if you guys can come up with or remember what the word for this type of solution would be. If I have one real solution, just kind of think about this. If this was 2, okay, one would look maybe, it's terrible, kind of like that. Okay, where we just bump the x-axis, right? You remember seeing stuff like that? Do you remember the word that we use for just bumping the x-axis or just touching it one time? So with a T. Talk about it in geometry, where a line touches a circle one time. Not transversal. It's part of sine, cosine, and tangent. Okay, so tangent, or having the parabola tangent to the x-axis is a visual for telling me I have one real solution. Okay. Does anybody remember though how many times that one real solution shows up in our algebra? If we go through the work by hand, we'll factor. So let's say that x value is 1. So when we factor this, we would get something that looks like x minus 1 times x minus 1. So how many times does that solution of 1 show up? 2 times. Okay? You guys remember hearing that? But it's the same number, so it's actually 2 solutions, but they're not distinct. They're not different. So we refer to it as one solution, one real solution. But we say that it is a double root. You guys remember hearing that phrase before last year? Okay. So that's a possibility. So I've had two distinct real solutions. I have one real solution. What's my next option? 0. So you get 0 real solutions, which defaults essentially to 2 non-real solutions. Okay? Non-real meaning that they're going to incorporate a negative square root in them. And you guys remember last year that brings in what number? Okay, it brings in your imaginary numbers. Okay, so and it actually takes us into dealing with things like a plus bi or a minus bi, that kind of stuff. Okay. Graphically speaking, kind of think about what's going on here with the pictures we already have. Okay, we start with this one, and we kind of slid it up to get that one with one solution, right? What's it going to look like if I keep going through that pattern, that process? It's going to look something like that, right? So, non-real solutions, or 0 real solutions, is going to look something like that, whatever my parabola may be. And right now I've got my parabolas as being concave up. They could be concave down. But my solutions, my real ones or my non-real ones, are all predicated on how many times I cross the x-axis. Okay? So as we're doing these equations, we could, when we factor a couple of these here in a little bit, we could at the onset graph them on any one of our tools and get our solutions and get what it looks like as a factor form. Okay? But I also want to make sure that we can actually go through the analytical part of it and go through the process, the procedures, the patterns to get our factor formats that way as well. Okay? So I'll give you some examples visually with a graph along with doing things by hand. Okay? You guys remember seeing that stuff before? Okay, good. All right, so that brings us to talking about a couple things down here. The 0 factor property is key to really factoring anything that we're going to deal with. Okay? And basically what the 0 factor property states is that if A times C equals 0, where A and C are elements of real numbers, then A equals 0 or C equals 0. Now actually let's make this and/or. There is one situation where they both equal 0. And that logic, that idea there, helps us decide what our solutions are, okay? But that only works when I have a 0 on the right-hand side, because it's a unique type of number, okay? If it was a non-zero number, there's actually no way for you deciding what one of those factors are, okay? So let me draw something up here. Let me write something. Basically, your A term here, when we use this, that thing there is going to be like an x plus whatever. Okay? This thing here is going to be an x plus whatever. Okay? And those plus whatevers might actually be negatives. Okay? But basically what it's saying is if those are equal to 0, if these are equal to 0, then you know that maybe the first one is equal to 0, or you know that the second one is equal to 0. Does that kind of make sense? Okay. Where if I had something like this, and with that being 0, that allows us to, if this one is equal to 0, it allows me to quickly solve for x there, right? Okay, and it narrows it down. It gives me one particular solution for that one, and then I can do the second thing with the second factor, or same thing with the second factor, and get a second solution. But if I say something like a times c equals 4, okay, you cannot narrow down and tell me exactly what a has to be or exactly what c has to be. Does that make sense? Like you can with it being equal to 0, okay? Because if I tell you two numbers that multiply together give you 0, we know one of them has to be 0. Okay? That's the only way you can get 0 through multiplication is if one of your factors is 0, right? But to get 4 through multiplication, there's a lot of options. A could be 4, C could be 1. We could flip-flop and say A is 1, C is 4. We could say A is 2, C is 2. And that already is a problem for us because we got a lot of options. Just 4 options is a lot more than what that is providing. But could I say that maybe A is, let's say, a half? So C could be 8. Does that make sense? I could say A is a quarter. So C is 16. I could do something silly and say A is a third. If A is a third, what times a third will give me 4? 12. Okay? So you can say, I'm going to let that number be anything I want to be. Then divide both sides by that number, and it gives you what C could be, right? And you can see that we can play that game forever, and we have an infinite number of options for A and C are. So we cannot narrow down what our two solutions would be if it was something like x plus 3 times x minus 4 equals 4. Okay? Does that kind of make sense? It has to equal 0 on the right-hand side. That's going to allow us to use this 0 product problem. Okay? And I use the phrase, this is a 0 factor property. I use the phrase 0 product property. The way I don't know, it's a textbook that I used when I grew up or whatever. Going up to 0 product property instead of 0 factor property. So if you hear me say that, that's what I'm talking about. All right, I want to talk about the number one technique that you guys know how to use in regards to factoring. And that occurs when we have something of the format with a 1 out here. 1x squared plus bx plus c equals 0. You guys use the phrase identify two numbers whose product equals c and whose sum equals b. Would you guys agree with that phrase? That's what we say all the time. One or two numbers multiply to give me c and add up to give me b. I want to talk about why that works. Why do we go through that? Okay? And I'm actually going to start with something in factored form. Okay? I'm going to start with something that looks like this. I'm going to just say x plus, I'm going to use a different variable, that's alpha. Okay? But it's just like any other variable, like a, b, c, d, whatever. I just want to use alpha in this case. And this would be x plus, we know that Greek letter? Beta. Okay? And we'll say it equals 0. Okay? If I have something in factored form like that, let's go through the process and kind of unfactor it, which would mean to do what to it? Oh, yeah, so I want to undo the factoring, so I've got to FOIL it, right? I've got to multiply it out. So if I multiply this thing out, it gives me x times x is going to be x squared, okay? x times beta gives me, we call it beta x. Okay. Alpha times x gives me alpha x. And then alpha times beta gives me, gives me alpha beta, right? You guys agree with that? Okay, we can do that FOIL pretty easily. Look at the middle two terms, the beta x and the alpha x. What do they have in common? They have an x in common, right? Okay, let's factor that x out. And now a lot of times when you factor things out, you would put the factor out front, right? That's kind of the common thing to do. I'm actually going to put the factor in the back. Okay? So like that. All right? And then I'm going to look at alpha beta there equals 0. So now what we've done is we've kind of rewritten what we have all the way at the top in blue. We have a 1x squared, right? But now we see that this term here, this b, is being composed of some alpha plus some beta, which are two other real numbers. Okay? And our c term, that one, is being represented by alpha times beta. Okay? The alpha times beta, the two components here, those alpha, or that alpha and that beta, are the exact same thing as that alpha and that beta, right? So they're factors that multiply together to give me c, aren't they? That kind of make sense? Or they're two terms, two numbers that multiply together to give me that c. And what do they do to get together here? They add together to provide me that b. Does that make sense, everybody? You see that link there? So that's why we can look through and say, okay, what are two numbers that multiply together to give me c and add to give me b? It's because of when we FOIL something that's in factored form, that's what shows up. And we can make that link between those components. Okay? But we have to have 0 on the right-hand side. If we don't have 0 on the right-hand side, we can't go through the algebraic or the analytical approach. Okay? I'm going to show you example 1 on the calculator first. Okay? And when I'm just going to use GeoGebra initially. And it's kind of a little bit more simplistic than maybe some of the other examples, and we'll see some of the other examples too. But remember what we talked about with linear equations, that the left-hand side of the equation is an individual graph. So I'm going to take y equals x squared plus 5x. All right, we get that parabola. I'm then going to take the equation y equals 24. All right, that's kind of a boring equation, y equals 24. It's just a horizontal line. Okay, now I've got to zoom out until I get to the y-axis to show 24 on it. Let me do this real quick. Let's go x-axis to y-axis. So I want that. Nope. We get those two curves intersecting, right? So the solutions to this equation, my x values to that thing, have to be the intersection of those two curves. And it's the x values of those intersections. So I'm looking, when we factor this, we should have 3 and -8 as answers. Does that make sense to everyone? Okay. Which that approach gives me a quick way for working through. A lot of times in some of our later procedures throughout the course, if an intermediate step is the factor, maybe using a calculator to get those results is much more efficient than actually going through the handwork. Does that make sense? Or the written work. All right, so if we're going to do this, we've got to get the right-hand side to be 0. Okay? And now, this is your C term, but it's composite. Okay? Meaning there are some terms that are not one in itself, okay, that multiply together to give me 24. So that's what I mean there, alpha and beta. Okay? One of those two factors that multiply together give me negative 24, but add up to give me 5. Yeah, 3 and 8, right? Which one's got to be positive? The 8's got to be positive, right? X plus 8, x minus 3 equals 0. Okay? Now at this stage here, if we go back up to the zero factor property that we had written out earlier, this is kind of your A term, and this is your C term, right? If they're going to multiply together to give me 0, what's that tell me about x plus 8? It has to be what? Or it could be what? Could be 0 itself. X minus 3 could be what? It could be 0. Okay? I have the word or here. So that gives me x to equal negative 8 and x to equal positive 3. Those are my two solutions. And they should work. I should be able to go back up to the original equation, plug in, for instance, just do one, it's easy, 3 on the left-hand side. 3 squared is 9, plus 5 times 3 is 15. 9 plus 15 equals 24. Okay, gives me a true statement. Negative a squared is 64. Plus 5 times negative 8 is negative 40. 64 plus negative 40, 24 again. So those solutions, plug back in, do satisfy that original equation. We can do that, right? We've done that in the past. Right? The number one thing that people mess up with throughout every year, I've always got about 40 to 50 college algebra students, and it always ends up about 5 to 6 of them will try to factor that thing without moving 24 over. Okay? They'll say, oh, I take an x out of both things on the left, and then they start dividing by weird things and get just answers that don't make any sense. Okay? You have to get 0 on one side. When we factor, guys, kind of I want to talk about a hierarchy of factoring techniques. Now, a hierarchy is kind of a list of things in regards to importance, right? Okay. One of the first things that you guys are always going to look for when we factor is a GCF. Okay. A greatest common factor. Okay. And that greatest common factor, a lot of times we're looking for it to be an integer, but down the road, it might be kind of a variable factor. It might be an integer coefficient in an x, or an integer coefficient in an x squared, or something like that. Basically what we want to do is, before we start doing any of our procedures of factor by grouping, AC method, any of that stuff, we want to see if there's a GCF. Because if I can pull that out of every single term, it makes things so much easier. Okay? So we're going to look for those. If there is no GCF, okay, the hope is that my A coefficient equals 1, and we can do the product sum technique. Okay? That's the hope. A lot of times, maybe we get an example like this, where my A coefficient is not 1, but if every one of those terms had a 5 in it, I can divide that GCF out and turn it into this, right? Okay, so we look for that. Hopefully it creates something like this, and we can start factoring. If that doesn't happen, we're going to go to what we call the AC method. Okay, sometimes you guys might have referred to that as or it develops a procedure that we call factor by grouping. Okay, now factor by grouping doesn't always have to start off with the AC method. Okay, you might be presented with a question right away where you don't have to do this, but you can still factor by grouping. Okay, so that's kind of the next thing. If that doesn't work, right now, and we'll add something in between here in a little bit, a couple days, maybe a couple weeks. You're probably going to turn to the quadratic formula. Okay, where I've got that arrow, we could put in things like the rational root theorem. You guys remember doing synthetic division last year? We put that in there, that all goes together. We put the square in there, but complete the square is kind of the same thing as quadratic formula. But that's kind of the hierarchy of factor that you want to go through. Okay? And you don't always want to go to the quadratic formula first. It is our catch-all. It will work all the time for quadratics. But it can be cumbersome. It can be a pain in the butt. It could take me 4 or 5 minutes to do a problem where if I maybe use the AC method or take a GCF out, I can get the answer in 20, 30 seconds. Okay, so you be careful with those things. And that's kind of the task at hand early on here is, can we be efficient? A lot of this stuff we know how to do already, but can we use it to benefit us efficiently? Because later on, when our questions are 20 minutes long to do, just because of the new math, we don't want to add to that 5 more minutes because I'm being silly with my factoring techniques. Does that make sense? Okay. So with this first one here, or sorry, example 2 here, I'm going to go through this and I'm going to say, okay, can I find a GCF? Is there something that divides every one of these things evenly? And when I say even, that's kind of a weird phrasing, probably not an accurate phrasing. We want to divide it so that there's a whole number left as a coefficient. Does that happen? No. Okay? So then I go down here, okay, well that's not going to provide a coefficient of 1 for A, so that gives me the AC method. So the AC method, remember this is your A term, this is your C term, you multiply them together. Okay? So that's going to give me negative 10, right? Alright, so now negative 10, we're going to kind of use that as the starting point for finding 2 numbers that multiply together to give me a number and add up to give me my B term. Okay? So what are 2 numbers that multiply together to give me negative 10? We're going to add up to give me my B term of negative 9. Negative 10 and 1. Okay, this one's kind of easy. So negative 10 and 1, those become my factors of negative 10 that add up to give me negative 9. So now what you do is you're going to rewrite this entire equation, 5x squared minus 9x, I'm not going to write 9x right now, and then minus 2 equals 0. So really don't change anything or anything that the equation does, but what this process here ends up doing for us is rewriting this negative 9x in a convenient way. Kind of uncombined like terms. Does that make sense to everybody? If I were to give you that last line I just wrote, that has 4 terms in it. Most of you would probably just start adding the x together, rewrite as 5x squared minus 9x minus 2. So you would combine the like terms. This procedure, the AC method, uncombines them in a useful manner. There's an infinite number of ways that I can uncombine negative 9x. Does that make sense? I can make it negative 10x and 1. I can make it negative 2x and negative 7x. I can make it negative, 13x and positive 4x. There's a lot of different ways to rewrite negative 9x as a sum of 2 numbers, right? But there's only one way to do that so that I can factor this problem. And that's the one way. Okay, so you have to do that. Every year, I get people just to think that negative 9x is just willy-nilly just say, oh, it's going to be negative 4 or negative 5. Okay? They have no logic behind it, no reasoning behind it. And obviously that's not going to allow you to factor correctly. Okay? So then we do factor by grouping. When we factor by grouping, and once you get in the habit of doing this, we're going to group those 2. Okay? And then we're going to group the back 2. But when you group the back 2, make sure you incorporate that plus sign or that minus sign. Get that thing to go away. Incorporate that plus sign or minus sign with that first term in the second grouping. It just makes things a little bit easier. When it's a plus sign, it's not a big deal. When it's a minus sign, people get thrown off all the time with it. Okay? But if we group it that way, it makes the process a little bit easier. All right. So now that we've done this, now you can start to look for a GCF. What is the GCF with these 2 terms? Okay, 5x. Okay? Now, remember, and I've told you this way back in geometry, factoring is a fancy word for what operation? For division, right? Fancy word for division. So when I say I factor out of 5x, I'm saying I divide it out of 5x. I'm dividing out of every single term. So what's 5x squared divided by 5x? Yeah, because think about this is what's happening. 5x squared divided by 5x. That's a factor of 1. Okay, x squared is actually x times x, right? Over the x now. Those cancel. And all up with x, right? So when we factor something out, we're just dividing, so we see what's left. And x is left. Negative 10x divided by 5x gives me negative 2x. Okay? I now look at this thing here. And I'm going to factor the green stuff by grouping as well. So try to find a GCF out of those. And when I start looking at that, nothing really comes to mind. So if nothing really comes to mind, or you can't really visualize what it is, what will always factor out? A 1. Okay? That's the one some people overlook. And then another way that I knew a 1 came out or should have come out is because I know what's supposed to happen here if this works. What's in these parentheses should end up being the same thing, right? Okay? Well, if I factor this first group, we got x minus 2, and then this second group is already x minus 2, then I can't change that, right? I don't want to change that. So divided by 1 will keep it the same. So now you guys remember that if these are identical, that becomes a factor. And then the objects that are on the outside, they become my other factor. Right? Okay? At this stage, guys, I think it's a good idea to check yourself. Okay? And even maybe once you factor these out, especially when that's not a 1, especially when that's negative, is to quickly redistribute things to see that you still have that line right there existing here, just written differently. Does that make sense? The reason I do, I kind of compare it to like putting a car on an assembly line at Ford or Honda or something like that. Every time a worker adds something to the car, they check it, right? They go through a quality control thing to make sure that that component works, right? If they do that for every component that they add to the car, when that car gets off the assembly line and goes out to the the dealership, the dealer can be guaranteed that when they turn the key to the car, it's going to turn on, right? If they just start adding stuff to these cars and they're not checking it at particular stages, and it gets out to the dealer and the dealer turns the key and it doesn't turn on, there's no way to troubleshoot on what was the component that's causing that car not to work, right? So they check it periodically. It stinks that when you go through a problem, you don't check it periodically when you can, and you're wrong at the end, okay? You got to redo the whole problem, right? Wouldn't it be nice to realize, oh, I'm only wrong like 2/3 of the way through. I've done 2/3 of the problem. That's all right. And here's where I made a mistake. Does that make sense? Okay. So I try to find my mistakes as I go instead of waiting until I get to the end and just knowing that I'm finally wrong with the end result. Okay. Now we've got the zero product property. We can say x minus 2 equals 0, and we can say 5x plus 1 equals 0. So x is 2, and x is negative 1/5. Is that all right? Okay. Here's my question. Does it matter how I wrote those here in the middle? Does it matter? Let's go through it. If that's the question, we've got one other option. We can rewrite it differently and just check to see if we get the same answer. If I go 5x squared plus 1x minus 10x minus 2 equals 0, right? We group these first two. And then, like I said, when you group the last two, group that sign right there with the last two. What can come out of the first two? Just x now, right? So leaves me 5x plus 1. Okay. What can come out of these two? Negative 2. What's that leave me with? 5x plus 1, right? Is this becoming a factor then? Just like it came a factor right there, right? Is x minus 2 a factor as well? Just like it was down here? So regardless of how I put those two terms, negative 10 and positive 1, do I still get the same factors as my neighbor who wanted to put them in a different order? Yeah, it's because of the commuter property. Negative 10x plus 1x, same thing as 1x minus 10x. So you can do that. It's just that you're going to find out that your groupings factor differently, and what's left in the parentheses in your factoring might be different. But collectively, your two groups of final factors are the same. Is that all right? So it doesn't matter. If for some reason you start going through factoring and you do not develop these two things to be the same, the sets of parentheses to be the same, factor by grouping probably doesn't work there. And a lot of times that's going to happen when the problem starts you off with 4 terms already. And we'll get to that at some point. But factor by grouping may sometimes provide us terms in those parentheses that are not the same. All right, what about this one? What do I need to do first here? Yeah, I need to distribute. I want to show you guys this graph first. I think it's important to look at this one because x squared is obviously a function that we're very familiar with. Okay. When I look at 5 times x plus 100, okay, that line is that blue line there, right? Okay. Now, if I'm just looking at my graph and trying to find solutions, that might be kind of hard to do here, especially on TI 83 or 84. GeoGebra does a good job of being able to quickly tell me those solutions. So negative 20 and 25 are my solutions to this equation, right? But what we do graphically, that blue line, our hand, or not graphically, analytically, by our handwritten algebra, that blue line, we want to adjust it because it's got a slope right now. It's kind of an ugly line. We want to try to adjust it to make it a really nice, convenient line. And that really, really nice, convenient line is a horizontal one. And the most convenient horizontal line is the what? The x-axis. Okay. So we're going to try to take that horizontal line and change it to the x-axis. Now, as we do that, the algebra is going to obviously change the parabola a little bit too, but it's going to maintain the parabola curvature. So what we do, we write this, obviously it's 5x plus 500, right? We'll move everything over. And I get that, okay? Something that I think we're all fairly familiar with. But I'm going to now show you what that would look like. X squared minus 5x minus 500. And then I'm going to graph y equals 0. Okay, so we got y equals 0 there. Now my parabola over here kind of a pretty steep. Got to go down to below negative 500 here for the vertex. But you see now that isn't it much easier to see where this orange parabola intersects this horizontal line y equals 0 than it was to see where this red parabola intersected the blue line? Does that kind of make sense to everybody? Okay. The intersection is still negative 20 and positive 25, right? Okay. Same solutions, different looking graphs, but it's more convenient this way. Especially when we start talking about inequalities, it's going to be so much more convenient to look at this yellow graph over here in contrast to the green one. All right, so now we got to think about factors that multiply together give you negative 500. Negative 500 is a large number, right? So it's got a lot of factors. The larger those numbers become, probably the more inundated with factors it is. Okay? So it's kind of a pain in the butt to write the list like 1 times 500, 2 times 250, okay? And so forth, 5 times 100. And you keep going all the way through and write them all down and see which ones actually give you negative 5. And this is a strategy you guys can use if you make the argument that that number right there is pretty large, that one's pretty small. Negative 5 is relatively small, okay? If negative 5 was 0, I'd be looking for the square root of 500 as my factor. Does that make sense? Okay? Because in those two things, one positive, one negative would have to give me 0. So -5 is a little bit bigger than 0, okay, in the negative direction. So what I'm going to do is I'm going to start off with trying to find, okay, the square root of 500. Just give me a starting point, okay? So 22.3 times 22.3 is going to give me about 500. But if one of those is positive, one of those is negative, it's going to give me 0. But what I know then is that if I start changing that 22.3 number to integers, okay, close to it, and divide 500 by it. So I'll take 500, we'll divide that by 22. And I'm going to look for a whole number output. That's not a whole number. So then I change that 22 to a 23. Not a whole number output. So I change it to 24. Not a whole number output. Change it to 25. Whole number output, right? Okay? So that technique tells me my two factors. One of them's 25, one of them's 20. One of them's got to be positive, one of them's got to be negative, right? 25's got to be negative. Okay? X minus 25, x plus 20. So then x equals 25, and x equals negative 20. That's a procedure, guys, that you can do all the time, but it's so much easier because of the kind of the iterations of checking, the 22, and the 23, and the 24, and the 25. The smaller that number is, that -5, the smaller that is, the less of those I have to check. Okay. If that number was negative 500 is my C, but the middle term was negative 499, I probably don't want to use this technique. Okay. I assigned 1.4. I think there's like 13 questions on it. That will be due Friday. Okay.